So this is the perfect place for me to actually start talking about. Okay, so let's recap. All the LRT tests that we have done basically circled around two things. Equation 652, set up the ratio. Be very careful in the maximizers of the likelihood under the conditions specified by the null and under the conditions specified by, well, unconstrained over the entire parameter space, capital omega. Doing that gets you the ratio that you need. The next step was, we know that it makes sense to say, reject the null if this ratio is small. The finding of a C is always the thing that makes the test useful to someone. You want to get someone an actual number that they can use so that when I get this, I'm going to reject the null. It's a test. So where we are going with, and this is the last page of our textbook thing, and you can see, right? Do you see all these things are actually done in the textbook that we were working on today, right? But I prefer to have you work it out in bite-sized pieces, because if you look at the way the textbook does it, it's next, consider this identity and all that. So that's why I do it the way I do. But basically, that's what the test was. Okay. So my last thing, which I'm going to teach you in this class, is this: what do you do if your likelihood ratio creates something that you don't know how it behaves probabilistically? What if it did not work out that it was t-distributed? Or something established that you somehow know how there are tables for, you can find a quantile for, and that's where this theorem comes in. I don't know why they don't give the name for this theorem. It's called Wilks Theorem, W-I-L-K-S. You can write that down if you want, but just so you know, this is Wilks Theorem. And what is Wilks Theorem? Wilks Theorem is amazing because it gets us out of a jam when you have finally worked out your likelihood ratio, but you don't recognize the thing that you have formed. You can't massage it anymore into something that you recognize. Well, Wilks' theorem comes to rescue. You know what Wilks says? Minus 2 ln lambda, that ratio, is approximately chi-square cubed. That's Wilks' theorem, and this is the last page of your notes. Wilks' theorem says that minus 2 of the log of the likelihood ratio that you have spent so much time constructing has a chi-square Q distribution. Why does it help us? Because if I know this, can't I work out, therefore, can I give someone a rule for what to do if I get a lambda value of a certain amount? I can. See, you worked out the lambda statistic. Then you said, reject null when lambda less than C. But that's not very helpful to someone, because unless you tell them what C is. And so you worked it out until you recognize that lambda can be massaged until it behaves like something that I can see. What Wilks is saying is fantastic. I know how minus 2 log lambda behaves without having to actually massage very much. It's chi-square C, chi-square Q, approximately. What's Q? Okay. The textbook really goes into a quite a detailed explanation. I will just, it's really easy. Q is the difference between the number of free parameters in the entire parameter space versus the number. So in the example where I constrain mu to be 5 versus when mu could be anything, the dimension, okay, and let me ask a question to the class. What's the dimension of the real line from a linear algebra standpoint? What is the dimension of the real line? Well, how can I say this? 1, right? Because the real line basis is built up of the vector, well, 1. This is a dot. What's the dimension of a set which is just a dot? 0. What's 1? I can't believe I'm saying this. What's 1 minus 0?
1.
That took too long. 1 minus 0 is 1. So Q, in the case of the problem we have just done, is 1. Because that's the difference in dimensionality under the null versus the alternative. Am I making sense? Yes. Notice the sigma squared part does not change. The sigma squared is any positive number. But the dimensionality of the mu part under the null versus the alternative is a different one. Because all real numbers, dimension is 1. A dot at just 5, dimension is 0. So 1 minus 0, 1. In other words, you can look at a chi-square 1 to get the approximate distribution of minus 2 log. You didn't have to know about the existence of a t distribution, in other words. But of course, the t is better to use when you can, because the t distribution is exact. This is only approximate. That's what that D arrow thing, which I've never explained, because we don't cover that in this class. This means convergence in distribution. You can just read it as approximately. Approximately, all right? So, I did say I don't want to go into. There's only there's only 2 more group works. They are both linked to this concept, Wilks theorem. So we will do this in our last class on Thursday. All right. So today's class will actually end early. And do you have any questions for me, right, about this before I say class is over? Any questions on this? Everything clear? Right? A lot to chew on, especially this difference in dimensionality, but give it a think. Okay, so basically, you need to be looking at a chi-square 1 if you wanted to do this using Wilks theorem's approximation. But it is an approximation, so it takes away the need to know about the t distribution at all. All right, so that's all for today. Next class will also be short because we will just finish this up for Wilks theorem. Like, pretend we don't, so just hang on to this. Pretend we don't know about the t distribution. What could we do? Right, basically. All right. Okay, that's all for today.